Parallelism is a really simple concept. Here we've got, well, it's a rectangle, and because it's a perfectly drawn rectangle produced on AutoCAD, I know that this line and this line are perfectly parallel, and I know that this line and this line are perfectly parallel. Very straightforward to draw. It's actually not quite so easy to machine something perfectly parallel. Very often what we end up with is something more like this. Okay, it's a little bit exaggerated, but we've produced a taper. Interestingly, it's fractionally more difficult to draw on AutoCAD than parallel lines, although it tends to be what by accident we produce on a machine. Now here we can see that yes, maybe this face and this face are perfectly parallel, but these two sides, the long sides where we've perhaps been machining, we've ended up producing the taper, and it is definitely narrower at this end than it is at that end. The other mistake we make in machining parallel faces is producing one of these. As I'm sure you're all aware, it's called a parallelogram because the two longest faces are perfectly parallel. And in fact, because the angles are the same, these two shorter faces are perfectly parallel. But one of the mistakes that we all tend to make is we associate parallelism with squareness. So in our original perfectly parallel rectangle, we have clearly defined square corners. This is 90 degrees, as is this, as is the other two. So we have a perfectly square parallel block. Here, under the parallel test, we could say yes, they're parallel. The sides are perfectly parallel to each other. But unless we start to introduce further measurements to check for squareness, we won't know exactly how accurate this block is. So the parallelogram is another mistake that's easy to make whilst machining if you don't measure everything carefully at every step that you take. And again, a quick look at the British Standard 8888 symbols shows you two, well, parallel lines being the standardized symbol for parallelism. Light skim on a bit of brass. Don't want it to take too much off the outside, so it's only a light cut. And quite slow feed. You don't want to watch this. I'll speed it up a bit. Still going. Oh, thank God for that. So finished our turning. We've probably been working to a drawing, so we had a dimension that we were aiming to achieve for this piece of brass. It's general that we will start our turning operations at this end, the end furthest away from the chuck. We would probably have taken a trial cut to get our finished dimension. We would have been very careful to make sure that this size was exactly as shown on the drawing. One of the major concerns when you're working over long distances like this, and this is comparatively quite a long distance, particularly for a small lathe, is that we've maintained that degree of parallelism, that we haven't turned a taper. So the next step obviously is to start to take some measurements to see how well we've actually been able to maintain that parallelism. First and foremost, we're going to use the micrometer. This is a 0 to 1 inch micrometer, and it actually measures down to tens of thousandths of an inch, so reasonably high degree of accuracy from this. And standard protocols for using a micrometer. So set it on the widest point, and then you can take the measurement. Now we can obviously read off the measurement from here, and then we can compare that against the drawing. There's a nice quick ready reference, if you like, sanity check that you can do right at this point without even bothering to read all of the complicated scales on your micrometer. Once we've set it at this dimension here, I can now take this device and I can move it further along, and I control it here maybe, and then I can go further along and I can try it here, and actually I can tell you there I can't really get that on. If I go even further, yeah, I definitely can't get it on. There's no way that that micrometer will fit over, and yet here I can just confirm that that's a nice friction fit that you would expect from a well set micrometer. So in essence, what we've done by setting it at this end and maybe locking it off just to confirm it doesn't move is we've made a go no go gauge. So I can really quickly, as I'm working, just set it at one end and then do a comparison check along the length of the shaft. And I can tell you that's a bit stiffer there. I can get it on, but only just. By the time I get to here, I would have to force it to push it on. So that instantly tells me, without taking a single measurement, that what we've got here is a taper. Now if we actually measure it, got 9686, so 0.9686 of an inch. Always when you're dealing with measuring tools like this, what we need to do, I'm going to actually move my thimble, I'm going to put it back on again, and I'm going to check, trying to be in exactly the same place as I was before, that I get exactly the same reading. I'm getting repeatability. 9686. So I've checked it twice, I've got the same figure. That tells me that dimension is pretty much spot on. And then I can work my way along the shaft, doing as many measurements as I feel is necessary to build up a map of its overall dimensions. So we are 968 9689. Nine six nine 9694. So we've definitely got a progression along here. It is definitely getting wider as we work our way along. Not massively so, but nevertheless, if the dimensional accuracy of this part was critical for its parallelism, for example, if we're making a locking pin for something that needs to slide into a close fitting hole, this dimension here may be correct, but if it gets bigger as it works its way down, there is a very high possibility that it will jam, which means it won't be able to perform its function as required. So there is a good example of the importance of parallelism and how we can check it in order to hopefully try and maintain it. So another way of measuring it is to use a DTI. So what I've done, I've set up my DTI here, and I've got it, if you think of your chuck like a clock, so we can think of this top position here as being 12 o'clock, underneath here being 6 o'clock, and then you've got 3 o'clock and 9 o'clock on the two sides. We need to come in at either 3 o'clock or 9 o'clock depending upon your setup. The way I am here for ease, I'm set up at the 3 o'clock position. So I've got the DTI, I've got it nice and square onto the material, as near as I can get it, and I've got it set on the centre line so that it will run nice and straight all the way along the centre line. Once you've got that set up, you can get a reasonable degree of accuracy from doing this. Zeroed it in. I know it's going to be very difficult for you to see it just because of the positioning of it, but this is where it really needs to be in order to get a decent figure. So we're on 0, and then just going to gradually rotate it through. I'm getting imperceptible movements on there, and got something in the order of just under a thou. so not a great deal of movement on the needle. Obviously if you've got appreciable taper, the needle will swing very wildly, and it will be easily noticeable. This gives you in some cases a quicker way of seeing if you've got a nice continuous taper along there rather than some form of step in there. It's not necessarily the best method of measuring it, probably go with a micrometer, but it is another option that you can use. This kind of setup where you've got the DTI in position here is actually very good if you need to make actual adjustments to the lathe to eliminate this taper. We've got a taper in there, we want to get rid of it. So the chances are the problem is the positioning of your tailstock here, and most tailstocks come with some adjustment screws that mean you can move them from side to side very slightly. And obviously you need to be able to measure that to make sure you've got it spot on. So with a known ground piece of bar held here, you would then be able to take measurements along here until you get zero deflection on your needle whatsoever, and you know that then the tailstock is perfectly true. There can be other issues. There is also a possibility that the taper isn't being produced by the tailstock being out, but it is actually produced by deviations from top to bottom. So as your cutter is moving along, it's maybe going up or it's going down, and it starts to cut deeper or shallower as it moves its way along. And that can actually be to do with some twist in the bed that's caused by the actual setting up of the machine in the first place. And you would then need to get some shop levels out and ensure that the bed is perfectly true and straight all the way through. In general, I'm reasonably pleased with that. For the age of the lathe, slightly less than a thousandth of an inch across that kind of length is, for the kind of work that I do, more than adequate. But it does go to show you that even over a small piece of material, taking a light cut, you can still get a tapering effect if you're not really careful in checking your machine.